Friends, in this lecture we will talk about some details on analysis of marine risers. We will also look into the types of marine risers, forces acting on risers and how to analyze them for the given set of environmental loads acting on the risers depending upon their profile and functional usage. First question, let us try to ask in mind is what are risers? Risers actually connect floating drilling or production platforms to the wells. They are meant for different purposes. One, they are meant for drilling. 2, completion or workover. 3, production or injection, and 4 for exporting. They are also subclassified. As low pressure and high pressure risers. Risers can be grouped in different forms. One, bundled risers. Flexible risers, top tensioned risers, TTR, steel catenary risers, SCR, and of course hybrid risers, which can be a combination of steel and flexible risers. Before we look into the methods of analyzing a riser, let us look few more details about these groups of risers. Let us start with a low pressure riser. Low pressure riser is one which is open to the atmospheric pressure at the top end. Essentially, they are useful for drilling. They have or they contain large diameter pipes. Large in sense, typical diameter of these kind of risers is about 500 mm. They also have lot of peripherals. What are the functions of these peripheral lines? The peripheral lines can be kill and choke lines, which are useful to circulate fluid when kick occurs in the well. They are also useful in communicating with the well about closure of BOP in case of a gas leak, or let us say in case of a gas kick. One can ask a question, why this should be communicated? Generally, in case of low pressure risers, BOPs are fixed to the sea floor. So, it becomes essential that the well remains in communication about the BOP closure, etc. So, you need peripheral lines to communicate this data. The next one could be booster line. They are useful to inject fluid at the lower end and to accelerate the flow. That is why they are called booster lines. Generally, when risers are to be installed at water depth more than 20 meters, they need to be top tensioned. Why top tension is required? Let us try to answer this question. Top tension is required to maintain stability of the riser when installed in higher water depths What is the top tension riser force? Generally, this force is equal to or marginally greater the sum of 1 weight of the riser equipment, 2 buoyancy force of the riser, 3 forces arise from waves and currents. So, now in case of deep water depths, the top tension force would be of a very high magnitude. It is not a healthy practice to have a large magnitude top tension forces in a given system, because applicability will be a big issue. In order to reduce this weight, this intensity, risers are provided. With buoyancy modules. Generally, buoyancy modules are provided in the upper part of the length of the riser. Now, the question is, what is the usefulness of buoyancy modules? There are many. First could be they are helpful in reducing top tension force that is required for the riser for installation of the riser, in particular in deep waters. That is the first advantage. The second advantage is they make the riser neutrally buoyant. International standards ISO 13624 1 2009 prescribes the procedure for design, selection, operation, and maintenance of marine risers The second one what we have is high pressure drilling riser. These risers are installed when the blowout preventer is located closer to the surface. So, that is a technical requirement and mandate to have a high pressure drilling riser. The second point with this kind of riser is these risers do not require any additional peripheral lines which are essentially useful for communicating with the blowout preventer. So, in this case BOP is located closer to the surface, as a result of which no additional peripherals are required when you use this kind of riser. Most importantly, these risers are designed to operate at full pressure. The next one what we have in the line is flexible risers. These risers are more useful as production riser or export riser. They are also useful in flow lines. Flexible risers are different in structural configuration from that of low pressure drilling risers. These risers, that is flexible riser, these risers have layered architecture. A typical cross section looks like this. This layer is the innermost layer of the flexible riser. So, flexible risers are layered. The inner metal surface is called carcass. So, I should say this is carcass. So, the carcass is covered by plastic pressure sheathing. This is required to assist fluid containment. So, there is a layer which is plastic pressure sheathing, So, this is plastic pressure sheathing layer, the one which is shown in green. The plastic pressure sheathing layer it will be further covered by a steel vault which is needed to sustain the high magnitude of hoop stress. So, I have one more layer which is steel vault. So, this layer is steel vault. Steel armors cover this layer. They are useful to improve resistance against axial, especially tensile stresses. So, I should have a steel armor in n layers to improve the resistance against axial tensile stresses of the riser. The whole cross section now will be covered by anti-wear layer. Is usually plastic outer sheathing. Okay, this is the anti-wear layer. Which is covering the entire cross section. The outer layer, this outer layer actually prevents seawater penetration into the riser. Let us talk about the next type, which is top tension risers. In fact, all risers are mostly top tension, because in order to balance their weight and buoyancy, a top tension force is applied when the riser is installed or commissioned at higher water depths. TTRs are required to ensure stability first TTR was commissioned in Huttal TLP in the year 1984. Top tension risers are risers that connect seabed through what we call as a stressed joint. In addition, these risers will also have what we call as a keel joint, which is located at the keel level of the platform. Let us quickly see the details of this graphically. Let us say this is the vessel, and this is my mean water level. I will have your drilling derrick, which will have a base housing through which a riser is connected. These risers will have top connection, usually a ball joint. They also have some counterweights which are called riser weights to hold down the riser in a specific profile geometry. They may also have buoyancy units to hold down the riser. Now, the riser is then connected through a bottom connector to the seabed, which is also through a ball joint, so that enough flexibility is introduced in the connection points between the riser at the top and the bottom ends of their connectivity. The distance with which the riser flows and connects to the seabed is called as an offset. The riser will be now subjected to high tensile force, riser tension. In addition, they will be subjected to wave loads. They will also be subjected to current loads, there is a very interesting design guideline what generally people used to follow in case of top tension riser. A very interesting and vital design parameter for a top tension riser is actually the ratio of top tension to its apparent weight. Usually for a good design this is kept between 1.2 to 1.8. It is very interesting to note that generally higher top tension is required and hence provided for platforms with large offset. Therefore, the main reason for this is they demand higher tension riser stiffness. In order to reduce this increased top tension, air cans are used. The most vital point in this case is, as these risers are highly flexible, in terms of its cross section, they undergo large deformations. And of course, finite rotations. So, in general, riser is a long, slender, vertical cylindrical pipe axial tension is generally provided to induce or improve total stiffness. Please understand, this varies non-linearly along the length of the riser Another assumption what we are going to make in the riser analysis is outer surface of the riser is generally not uniform, but we idealize this to be uniform. Friends, in the analysis, risers are actually subjected to waves and current from different directions. But for analysis, it is considered to bend in any one plane where plane of motion of the platform is traced. That is a very interesting and important statement in the analysis of marine risers. Of course, to account for wave direction effects in the riser analysis, one can do a coupled analysis of the risers under different such bending planes. But at a time only one plane is considered where the platform of the motion is traced. So, we should now draw a free body diagram of a segment of a riser and try to derive the governing equation which gives me the stresses on the risers. Let us say this is my xy plane and this indicates segment of a riser. So, this is a point which gives me the radius of curvature of the riser, and the initial segment is at theta and the total segment is at d theta by 2 from both sides, and at this point we have Fys, Fw acting vertically and horizontally, and horizontal is Fxs and Fts, where this point is considered to be S. There are differential forces which are acting as Fa minus dFA by 2 and Fa plus dFA by 2, and the moments could be mb minus dmb by 2 and this could be mb plus dMb by 2. There again could be Fs minus dFs by 2 and Fs plus dFs by 2. This is a typical free body diagram of a riser segment. The segmental length of the riser is ds. The external forces acting on this segmental length of the riser is ds. The external forces acting on the segment are both in horizontal and vertical directions, which is Fxs and Fys respectively. Fw is the weight of the segment acting at the midpoint. Internal forces, these are external forces, internal forces that act on the segment are shear, bending moment and axial force, as you see in the figure adjacent to the screen, which is Fs, Mb and Fa. So, the equilibrium equation in the horizontal, vertical and angular directions are given, let us say as below. Let F1 be dFa by ds minus Fs d theta by ds, and F2 be dFs by ds plus Fa d theta by ds. Let us say algebraic sum of all forces in the vertical direction is 0, looking at this figure. Okay. So, now I should say F1 cos theta minus F2 sin theta. I can see the figure here. The angle of this is theta. We are resolving it in the vertical direction. F1 consists of both Fa and Fs. In fact, both F1 and F2 consists of Fa and Fs. Fa and Fs are the axial force and the shear force acting in the system. So, therefore, sigma Fi 0 F1 cos theta minus F2 sin theta minus Fw plus Fys is 0. You can see here Fw is acting downward and Fys is acting upward. So, minus Fw plus Fy is 0. Similarly, if I write sigma fx 0, this should be f1 sin theta plus f2 cos theta plus fxs minus mx double dot should be 0. If we talk about algebraic sum of moments 0, then we should say dmb by ds plus fs should be 0. I call this set of equations as 3. In this equation, small m denotes mass per unit length of the segment. It is also assumed that the riser undergoes small deflection. Hence, we will continue to apply small deflection theory rather small deflection beam theory to the system. So, friends, in this lecture we discussed about the types of marine risers. We picked up a segment of the riser, we explained the forces acting on the segment of the riser, and we are now going to apply small deflection beam theory to derive vital equations that govern the response behavior of this riser under the given set of forces as shown in the free body diagram on the screen, which we will continue and discuss in the next lecture. Thank you.